Hi, in this video, we will be making an ExtendSim model of this loan process example that you see on the screen. So here, basically, the idea is a loan application file comes here in the first process. The worker in 15 minutes checks the loan documents, puts them in order. That goes to the second workstation where the loan officer categorizes the loan, and then they split into two parts. Part of the file goes on the upper path for check for the credit rating, and part of the file goes on the lower path for data entry into the system. After this, these both get combined, and the file gets combined again, and then the last step in the process basically completes the paperwork for the new loan. The times are defined here in each of the blocks, and we'll say these are the mean times, and all of them follow an exponential distribution with the provided means on this slide. As you can see, the cycle time on this would be 60 cycle time, or let's more specifically what we call throughput time. It is also in ExtendSim terminology, it would be called cycle time. And basically that's the time one file will take to complete the process, and that would be 15 plus 20 plus 15, because among these parallel paths that we take the longer path, plus 10, and so it's a 60-minute cycle time without any wait involved. Of course, when we add the waiting time, it will be a lot longer. And so let's say the manager says as long as it gets done in 2 hours, so twice the theoretical throughput time here, as long as it gets done in 2 hours, 120 minutes, we are okay. But beyond that, the manager wants to know what is that time. If it goes beyond 2 hours, what's the average required? What's the average time for that case? So that's what we'll calculate. We'll model the process and try to determine that when how often is the process time longer than 2 hours, and what's the overall process average time, assuming that anything less than 2 hours, we just count that as a 2-hour cycle time. So let's get to our worksheet here and get into making this model. We'll use a create block for the arrivals. And so here we go, we take create block, put that here. Yep, I guess with this here. And so a create block will, let's assume an exponential distribution with an arrival rate mean of, let's say 30 minutes, because we have our bottleneck process at 20 minutes average. And so our arrivals have to be at a slower rate than that. And so we'll assume our inter-arrival times are 30 minutes. Okay. You can also actually define, before we leave this, a timing attribute. That's where we'll track the simulation, the cycle time, and so we'll call it cycle time. Okay, and so then we'll set up the rest of the processes, and we'll just use the workstation rather than include adding both individually the queue block and the activity block one at a time. We'll just do this. And so after the first two processes, if you remember, well, we can look at that. After the first two processes, the file splits into two components. One goes on the upper path, one goes on the lower path. So for doing that, we'll need an unbatch block right here. And that allows us to then split one job into its components, or one flow unit item, one item that's flowing through, into two paths. And so we will use this, maybe this highlighting the mouse is not such a great idea. Let me see if I can change the settings on this. That didn't work. Step square. Okay, we'll go with this little mouse then. So we'll go and pull down. Oh boy, this is even worse. Okay, let's see here. Okay, so we'll use a pull down here so that we can get two outputs. So because we want to split it in two paths, if we wanted to split into more components going to say three parallel parts of the process, we'll pull down that and make three output ports here, or output connectors as it's called. So we got two paths in this case, and then we'll put our workstations for these two paths and connect them to mimic the process that we are modeling. And after this, they need to combine back together into one file in this case. So we have two components of the job or the item going into two parallel paths, and we want to combine them back. And so for that, and in this case, we need to make sure that the components of the same file get connected back together, and not that we have, half of one file getting merged with another half of another file, or just two halves of the first file that's going on top or the bottom, they get combined into one file. And so for that, ExtendSim has a particular capability called queue matching. And so what queue matching does is make sure that the correct components get connected back together. And so we'll do that here. First, we'll bring these guys into this. And this block does have a capability to then put them together also, or just have them wait in separate queues. Everything coming from the first upper path will wait in one queue. Everything coming down with the second path, going down will wait in the second queue. And then across the two queues, it will match them. It can batch them too, but it works out better to show that explicitly outside. So we'll have a separate batch block following this block. In terms of settings here, what we'll do is we'll disable the batching. So we will have the batching done outside. And so when you disable the batching, then that's what it looks like, the icon. And it will now have two outputs because we have two inputs coming in. And so now we'll use a batch block to combine these two together. Let's see. Yeah, so we'll have to bring another connector in here and combine this. So now we have batched the application file together. And so we have one more step in the process here. We'll add that here, one more step. And finally, it will exit the system. So first let's do that, and then we'll go back and add information collection in this case. But here, for example, we just want to exit the system. So this is a representation of the process that we had in this example in the notebook here. And so now let's go ahead. Remember, we said manager would like to know that how often the cycle time is longer than twice the theoretical cycle time, which is 120 minutes. So we'll set up a structure, capture that. So for bringing in calculating cycle time, we'll first stamp the entry time in here using in an attribute. And for that, we will use the set block. So we added the set block here, and what we'll do, we'll stamp it with the entry time that we can use later to capture the cycle time. And so entry time is we say we want the current time going in. And so we'll use from the value library the simulation variable. So simulation variable is here. and we set it to time, and that is taking the time getting stamped into this. And then here we want that stamped into the cycle time. So we are saying that whatever is coming through connector 1 goes into the cycle time property. Okay. And at the other end, we will then calculate the cycle time. And so let me add that here. Let's make this a little bit closer here to provide some room. And so I'll add information block for that. No, that's in the, so if we are adding something in the path that the item is flowing, so we for those blocks, we go to the item block. And so here we have, oops, information is further up here, information block. Okay, so that's connected. And then we'd have to read cycle time off this one. So we'll go ahead and set the options here. Options reports current cycle time, because we want to find each individual cycle time rather than the average. And we need to identify where is what's the timing attribute. That's cycle time with our timing attribute. Okay. And then from here, we can read the average cycle time out. Not average, sorry, actual cycle time. So before we start collecting more logic, let's just run this and make sure that we are reading some cycle times. Oh, by the way, I've left the default setting here, which is running for 1000 minutes and so on. I guess we can change this at least 2 minutes. It just reminded me that I have not even specified the process time, so let's do that. This is specified a distribution. We are doing exponentials, 15 minutes. In this case, the first step is 15 minutes. Second step is 20 minutes, which is our bottleneck. The step on the upper path was 15 minutes. And on the lower path was 12 minutes. And so we are saying whatever on the chart that you are looking at in the notebook, these are mean times with the exponential distribution. And finally, the last process was 10 minutes. Okay. So let's now run it again. And I guess for initial run, it helps to see that things are kind of traveling down correctly, and seems like we can of course slow it down, but it's seems like it's going. They're not just queuing up at one place and so on. So that looked okay. Let's make sure that we are getting a value in our cycle time. Current is 104. Average is 122. So it seems like from this, there will be only a few, in this run at least, that went beyond our cutoff of 120 minutes. Okay, so let's go ahead and now put some logic into capturing how many exactly were above that 120 minute. So there are multiple ways of doing this. In this case, I want to show how to use the Max/Min block, maximum and minimum block, so I'll use that. And that probably is not the best way for doing this, but as I want to demonstrate the max and min block here. So we are putting this in here, and I will just reverse this so that we can kind of go back this way rather than stretching out on the right side where we might then need to scroll back and forth. So I'm going to do a right click and say default view reverse. So in the default view, inputs are from the left side, outputs are on the right side. But when I reverse it, the inputs are on the right side and outputs are on the left side. And so I'm doing this so that I can read the cycle time in here. So we'll do cycle time as well as we'll put a constant value in here because we want to see value more than 120 minutes. And so let's put the constant in here and we'll set that to 120 minutes. Okay, and I'm leaving that as in the default view because I can just connect this then from the right side of this to right side of this. And we'll take the cycle time in from the second excuse me, input. And so what this max block will do, and we have to make sure now it's set to output the maximum value. And so it will compare the two values and set out the higher value from the upper output. And on the lower output, it shows which of the inputs had the higher value. And so that we can use to actually count how many were higher than 120 minutes. And so first let's just first capture the average in outside of from the output from the mean from the max. And okay, well actually we need to escape and change this to default view so I can put in the input from the side. For counting, there's this block called holding tank, and that basically whatever value you feed in, let me default reverse on this, whatever value you feed in, it will just keep counting those, keep adding those to whatever previous value was there. And so basically every time we have cycle time which is more than 120 units, that is coming through this connector 1. And so this will say that it will send out a 1, basically saying that the higher value came in from connector 1. So every time this cycle time is higher than 120, it will keep sending a 1 out this way. And so we'll keep counting how many came through here. We can always look at the value in here, or we can display that value without having to go inside using this block, display value. Again, we'll reverse it so we can just feed the value from the left here, from the right. Okay, so this will show us the value of how many were above 120. And so now in this case, by the way, so again pointing out that all these gray blocks, while they can connect through some connectors into the overall flow of items, but they cannot be placed right on the flow path. They are generally connected through these value connectors. Like here, time is being connected so that we can read a value into an attribute of that item that's flowing down the line. So these are generally logical calculations of the main flow path. Okay, so now if we run, we will see the numbers, of course, are going up, and maybe now I can cut off the animation. Oops, we didn't get nothing, or what happened here? We got 21. Why did it display it here? Let's see. Options, input value, dialog open, model. Maybe when I turned the animation off, that kind of affected that. So let me just run it one more time. Oh, this time there's only one. That was more than 120. Let's see if that seems right or not. Let's check in here. What's our average? Oh, average mean is 120. And so that's why we only got one above 120. Well, actually, no, if the mean is 120, we should have got a lot more. We have total observations 26, which is correct. 26 units went through. So that's interesting that it's telling us only one was higher than maybe. Let's check the logic here. Okay, let's check the average without the cutoff. So maximum is only 130. Oh, of course, the average here, let's first talk about here. So here, our average turned out to be 70, maximum was 130, minimum is 8. And so when we did that cutoff to 120, so that we were saying minimum values get kind of updated to 120, and anything above 120 goes in as raw. And so there's only one value which turned out to be more than one. So this 2 hour time is working out to be pretty good estimate of most values would be under 120. But let's make of course this is just one set of random numbers. Let's try another one. This time, see, out of 20 we got 7 which were more than 120. 7 units that took more cycle time more than 120. And average in this case, if you're just counting anything lower as 120, was 125. So it's still pretty close to the only couple values. Well, even though 7 values went up, they were not too far off 120. Okay, so anyway, that discussion is just a made up requirement of figuring out how many are actually taking more than twice the theoretical cycle time. And so, but this idea was to show the usage of batch and unbatch and batch blocks, the usage of the MatchingQ block, as well as the Max&Min block on how you connect it to data and use the output. And that's about it for this video.